Welcome everyone. Welcome to today's session, and today's session is going to be little difficult. The session is most important for CSIR net aspirants. The question comes from this topic from last two papers. The question is coming in 2024 in June. The question was there in December 2023. The question was there, and when the question is asked from this topic, usually students do not understand that exactly from what topic the question is. Okay, many people confuse it with the scattering theory, but this question is not from scattering theory. The topic that we are going to cover is basically scattering from a Dirac potential. So we will consider the Dirac potential, and then there are two kinds of states which are possible in Dirac potential. Number one is a bound state, and number two is a scattering state. We will study both of them. Clear? So let's begin. So what is Dirac potential? So Dirac potential is, first of all, is written like this: V equals to minus lambda into delta x. Now delta x has a very special feature that delta x is 0 when is not 0. So at anywhere else, at when x is not 0, delta x is 0. But delta x is infinite when x is 0. So exactly at x equals to 0, your potential will be infinite, or your function will be infinite. Since there is minus lambda multiplied here, so infinity will become minus infinity. That is why you see the graph here. So you see a red line. So everywhere else the potential is 0, but at exactly at x equals to 0, you see a negative infinity. Because this red line basically shows that your graph is going towards a negative infinity. So consider it like an infinite depth well. So you are coming like this. So you are coming, and then in front of you is a well. The depth of this well is infinite. It's infinitely deep. So that is deducted. And the width is almost 0. So this width is almost 0. The width is almost 0, but the depth is almost infinite. So think of it like a well. The well has a almost 0 width but infinite depth. So that is something we study. Now, two possibilities exist when you are studying the system. So let's say you have this system, and then the particle is coming like this. So two kind of possibilities are there. First is that your energy is negative, and one is that your energy is positive. If your energy is positive, then you get a scattering state. So your particle will actually come and it will reflect back, or it will transmit over. So if the particle is coming and you have a well like this, then some part of the particle will reflect back and some part will transmit. This cannot be explained using the classical physics. Can you imagine that you are going on a straight road and there is a well, and because of that well you reflects back? That does not make sense in classical physics. You are going in a straight road, there was a well in front of you, and the well has an infinite width, but instead of just crossing that well, you reflect back. So some part it will be reflected back and some part will be transmitted. It will go on the other side. So that can only happen in quantum mechanics, and in quantum mechanics this actually happens. So when your energy is actually positive, means when you have a positive energy, in that case what you get is a scattering state. And that is our today's purpose. We will study what are scattering states and how to calculate. But if your energy is negative, in that case you get is a bound state. Yeah, bound state basically means that you are within this basically well, or you're bound within a limited region. So in Dirac delta potential, only one bound state exists, and the energy of that is minus lambda square m by 2 h cut. I have already taken a lecture on this. You can watch in my course where I have taken a full lecture on bound state of Dirac delta potential. So the only one bound state exists, and the bound state is basically minus lambda square m by 2 h cut square. That will be the energy of that bound state, and this will be the wave function of that bound state. Wave function of the bound state will be under root of gamma e ki power minus gamma root x mod x, sorry. And if I try to plot you this, so graph will look something like this. This will be the graph of the wave function. Clear? So you can clearly see that this wave function is sort of limited in a region. Okay? So the gamma can be written like this. Gamma is under root of minus 2 me by h cut. This is some facts that you should know by heart. Bound state solution is so crucial that it is even asked in GATE examination and in JEST and TIFR exams as well. But scattering state solutions are something which are only asked in CSIR net, especially in part C. So what do we learn till now? That your particle is coming, there is a Dirac delta well is there, and the Dirac delta well is at x equals to 0, so it is going down. And then if your energy is greater than 0, then you will have a scattering solution. Scattering solution means some part will reflect back, some part will transmit. But if your energy is negative, in that case, basically what you will have is that you will have a bound state. You will have the bound state, and there is only one bound state possible. The energy of that bound state is given, the wave function of that bound state is given. Now we are interested in the scattering state, and we need to drive it. We will drive everything from the scratch. Okay? And in this class, I'm going to go through a very long derivation, and each step of the derivation, we will have a physical meaning of those mathematics. So always we begin by, whenever we have to solve a problem, we begin by starting with the Schrodinger equation. So we write the Schrodinger wave equation. So this is my Schrodinger wave equation. Minus h cut square by 2m d square phi by dx square. My kinetic energy part plus v phi. My potential energy part equals to E phi. E phi is the total energy part. So this is my well, infinite well, zero thickness, basically Dirac potential. So if I talk about x less than 0, in this region the potential is 0. In this region also the potential is 0. So let's first solve the problem for x less than 0 and x greater than 0. Okay? So at x less than 0 the potential is 0. So I can put my potential 0 here. This will be 0. So you will get d square phi by dx square minus 2m by h cut square. I can take on other side. So you will get minus 2me by h cut square into phi. Now I can use little trick, and I can basically say that k is under root of 2me by h cut square. So I can define a new parameter so that I do not have to write again and again such long words. So what I can say is that k is actually under root of 2me by h cut square. Hence this thing can be written as k square into phi. Now this is an equation of a simple harmonic motion. If you are preparing for CSN at part C, at least this much you should know. Whenever you get an equation d square phi by dx square equals to minus omega square x or k square x or any square x, this is basically an equation of simple harmonic motion, or you can say is a harmonic solution. So the solution will be written as a into e ki power iota kx plus b into e ki power minus iota k. So it is a superposition. What is the meaning? What is this term and what is this term? What is the physical meaning of these? So a to power e ki power iota kx basically means the particle coming. This is an incoming particle. Okay? The wave which was coming. So rather than talking in terms of particle, I should talk in terms of wave. So the wave which was coming. B into e to the power minus iota kx means the wave which was reflected back. So when the wave was going, some part will transmit. On the other hand, some part will reflect back. Okay. So B into e to the power minus iota kx means the wave which was reflected back. Okay. So that is the meaning of this. So on left hand side, you can have two waves, one incident and one reflected back. Perfect. Yeah. So similar kind of solution will be there for x greater than 0 also, because at x greater than 0 also the potential is 0. Potential is still 0 at x greater than 0. So if I say I write the similar solution, so phi x will be c into iota kx plus d into minus iota kx. Perfectly fine. Now let's understand this. C into iota kx makes sense because this is transmitted. D into minus iota kx makes no sense. So this will be 0 because it will not make sense in this case, because if your particle is coming from left hand side, right? So some part will transmit. So I understand that it is c into e to the power iota kx, but d does not make sense. This term will make sense if your particle is coming from this side. the particle was coming from right hand side, in that case, it will make sense, right? In that case, your D and C will exist, but A will not make any sense. Okay? But right now we are considering that the particle is coming from left hand side. So A part was coming, B was reflected back, and C is transmitted. In this case, the D thing will be 0. Okay. So ultimately you will see that I will bring my D to 0. So this I will bring as 0 because it does not make any sense. A is coming, B is coming back and transmitted. So there is no physical reality about D. So this should go to 0. Clear? Very nice. Now we want to know, what do we want to know? So we know the wave function on left hand side, we know the wave function on right hand side. Basically I want to know three parameters, A, B and C. Okay. So what I want to do is I want to write B in terms of A and I also want to write C in terms of A. Basically if I give you A, how much energy was coming or what was an amplitude which was coming. So how much amplitude will be reflected and how much amplitude will be transmitted, which is also known as reflection and transmission probabilities. What is the probability that your particle will reflect back and what is the probability that your particle will transmit? Okay, so that is very simple concept. What will happen? How do we write B in terms of A and C in terms of A? A can be anything. A is in your hand, so A depends upon the incoming wave. So when your wave is incoming, that wave can have any amplitude. Let's say the wave has 10 amplitude. So what we want to do is we want to write our B and C in terms of A. That will tell us how much percentage is reflected and how much percentage is transmitted. Okay. So whenever we have to obtain these constants, we use boundary condition because the solutions are there. But in order to obtain this A, B, C, D, D is 0, we use boundary condition. So let's use boundary condition. Right. So first boundary condition is that wave function must be continuous. Wave function is continuous at x equals to 0. So at x equals to 0, left hand side wave function will be equals to right hand side wave. So phi 1 at x0 and phi 2 at x0 should be equal. If you put x0 in this case, you will get, sorry, very sorry that if you put x0 in this case, you will get a keep e ki power 0 1 e ki power 0 1. So basically you will get a plus b. You will basically get a plus b. And here also if you will put 0 and 0, you will get c plus d. I am making d 0 because if the scattering is happening from the left hand side, d must be 0. That is okay, that we already understood. So what we obtained actually is that a plus b is equals to c. That is my equation 1 and we will use it later on. Okay? We will use it later on and this is obtained because the wave function is continuous everywhere. If it is continuous everywhere, it should also be continuous at x equals to 0. Perfectly makes sense. Now comes the next part. What about d phi by dx? Differentiation of wave function will not be continuous. In this case, it will not be continuous. Because whenever the potential is infinite, the derivative of the wave function is not continuous. D phi by dx is continuous if potential is finite, but it is discontinuous if potential is infinite. And in our case, potential is infinite. As you know, at x equals to 0, potential is minus infinity. So it makes perfectly sense that d phi by dx will not be continuous. But we want to use this. If it is discontinuous, how much is the discontinuity? Discontinuous basically means that if left hand side has a value 2, the right hand side also should have the value 2 at the boundary. But let's say that both of them are not same. How much is the discontinuity? If the left hand side is 2, then right hand side is 5. So the discontinuity is 3. So what is exact discontinuity? So here we use a very special mathematics technique, which we say is integrating in a very small region. So this is my well. So I will integrate, instead of just taking x equals to 0, I will take a very small width from minus epsilon to plus epsilon. And I will integrate my wave function over this region. So I start with my Schrodinger equation and I just integrate. If I integrate in a very small region, that is a special technique. You should know about this. And if in interviews they ask you, find the discontinuity, you can use this. So just integrate. So you can go from minus epsilon to plus epsilon. d square phi by dx square into dx. Then you can put the value of potential. Potential is actually minus lambda delta x phi x into dx minus infinity to infinity, and then e into phi into dx minus epsilon to epsilon. This thing should be 0. Why? Because this dx is 0, almost 0, because the width is very small. So dx is very, very small. Dx is almost 0. But phi is a finite number. Wave function is a finite. Wave function cannot be infinite. That is a number one property of wave function. Wave function should be well behaved everywhere. So wave function should be finite everywhere. So wave function will have some fixed value at in this region. So let's say 1, 2, 3, 4. But this region itself is very, very small. It is almost 0. So when you multiply 0 with some constant number, it will be 0. So this thing will be 0. Right hand side is 0 because you are multiplying a finite number, which is a wave function, with the 0, which is a dx, almost 0, right? Because if you put limit epsilon approaches to 0, then this thing will go to 0. Otherwise it is not 0, but if you put epsilon going to 0, then it will be 0. Okay, perfect. So this goes to 0, so that is gone. So now we are left with these two things, integral 1 and integral 2. Integral 1 is simple. So minus h cut square by 2m comes as such. As you can see, the integration of double derivative is a single derivative. So you can see d phi by dx, and then you put a limit, upper limit minus lower limit. Upper limit means you are on right hand side, right? On right hand side, and lower limit means you are on left hand side. Okay? And here I can use Dirac delta property. You know the property delta x into fx into dx equals to f of 0. Right? This is a property. You know this property, right? This is a fundamental property of a Dirac delta, that delta x into some function fx into dx is equals to f of 0. So here it will be minus lambda will come as such. Basically, if I take it on other side, then it will become plus lambda, and delta x into phi x will become phi of 0. Phi of 0 means wave function at 0. What is the value of wave function at 0? Okay, perfect. So then again I can bring this minus h cut square on other side. So I will get minus 2m lambda by h cut square, and then I get phi of 0, which makes perfect sense. And then I just use this. So this will give me d phi 2 by dx minus d phi 1 by dx. Upper limit minus lower limit. So upper limit will be d phi 2 by dx, and lower limit will be d phi 1 by dx. Right? Right hand side minus left hand side. So this is the discontinuity in differentiation, derivative of wave function. This is exactly the discontinuity I was talking about, right? So what is the difference in derivative on right hand side minus left hand side? And it is equals to minus 2m lambda by h cut square into phi of 0. Okay. So now let me write it. So phi 2 was what? Phi 2 was c into e ki power iota kx, and phi 1 was what? Phi 1 was a into e ki power iota kx plus b into e ki power minus iota k. So let's differentiate. If you differentiate, you will get c into iota k, and if you put x equals to 0, which is our concerned point, then it will almost be e ki power 0 will be 1. Okay, then minus, and then you differentiate this, so you get a ki power iota k plus b ki power minus iota k. Exponentials are becoming 1 because if you put x 0, exponential become 1, right? And then this thing is as such. So then I can just take iota k common. I will get b plus c minus a, simple. Then right hand side is this. Then what I can do is I can take k on other side. And now what is phi of 0? Phi of 0. So basically, what is a wave function at 0? So either you can use this or you can use this, because wave function will be continuous. So it does not matter which one you are using, both of them will give you the same value. Okay? So what you can do here is you can put a plus b here, because if you put 0 in this, you get a plus b. If you put 0 here, you get c, and you know that c is equal to a plus b. So either you write c or you write a plus b, it does not matter. So I am choosing to write a plus b, so let's write a plus b. So wave function at 0 is either a plus b or c, both are same. Okay. Then again, to avoid some problems, I can say that let's say m lambda by k h cut square is beta. This is a very standard process, so that we don't have to repeat the steps again and again. So what I can say is m lambda by h cut square k, let's call it as beta. So what you get? You get simple concept, and then you can just play around. So you get iota c, right? So you get minus, so this is beta, right? So you get minus 2 beta a minus 2 beta b, and then iota a can be taken on other side, so you get plus iota a, and then iota c can also be taken on other side, so you get minus iota, no, c is here, so iota b can be taken on other side, so you get minus iota b. Yeah, so iota c remains iota c, and then you can take a and b common. If you take a common, you get iota minus 2b. If you take b common, you get iota plus 2b. Okay. In the next step, I am taking iota on other side. So if I take iota on other side, basically you can try this out and you will get this. So you will get c equals to a 1 plus 2 iota b, and because you know iota by iota is 1, but 1 by iota is minus iota. 1 by iota is minus iota because 1 by iota can be multiplied and divided by iota. So this iota remains iota, but iota square becomes minus. So it is minus iota. Okay. So whenever you have 1 by iota, you can write it as minus iota. Perfect. So basically what I have done actually is that I have obtained the relation between C, A and B. So this is my equation number 2. You already know the equation number 1, C equals to A plus B. So now I have two equations and I need to solve them. So what I will say is that from this equation, I can say that my B is equals to C minus A, and then I can put it here. So that is exactly what I have done. I have put it here. So then I rearrange, that is your duty. Rearrange here and there, and then you will get your relation between C and A. And that is exactly what I want. C is equals to A by 1 minus iota beta. Okay. And similarly, if you put it in the equation, you will also get B. So B will be iota BA by 1 minus iota beta. So these two are the most important results we have obtained. C in terms of A tells you that what is the chances that you will get a, basically A is the incident amplitude, B is the reflected amplitude, C is the transmitted amplitude. I have written C and B in terms of A, and this I need to remember, because in an exam you might not be able to do perform this entire derivation, so you need to remember this result. Okay, perfect. So we obtained this. What next? So what next is actually, this is known as incoming amplitude, reflected amplitude, and transmission. Now we will find transmission and reflection coefficient. The reflection coefficient is basically beta square by A ka square. B is the modulus, A is also modulus. This basically tells you that what fraction of wave will be, what fraction of energy will be reflected, and transmission coefficient is C ka square by A ka square, which basically tells you what fraction of energy will be transmitted. Okay, so let's first find B ka modulus ka square. So that I have done here. So how do you find the modulus of iota B by 1 minus iota B? So whenever you have to find the modulus of any complex number, so you basically do C bar into C. That's C bar into C. So first we will do the bar of this. Bar means converting iota into minus iota. So you will get minus iota B by 1 plus iota B, and then you can write this thing as such. So this will give you beta square by 1 plus beta square. That is what you can see. So what is my reflection coefficient? My reflection coefficient is beta square by 1 plus beta square. Similarly, my transmission coefficient is just 1 by 1 plus beta square. This is my transmission coefficient. So transmission coefficient is just 1 by 1 plus beta. That is the most important result. The transmission coefficient is 1 by 1 plus beta square, and reflection coefficient is beta square by 1 plus beta. So how much part will be reflected and how much part will be transmitted will be coming from this. Sometimes you need amplitudes, which we have done here, and sometimes you need reflection and transmission coefficients, which we have done here. Okay, I will suggest every student to do this derivation once without looking at the notes and try to repeat this, and then the results you can remember very easily. Now it is good to know what is beta, right? So So beta was m lambda by h cut square k as we defined it. And we already know what is k. K is under root 2 me by h cut square. So if you just rearrange, you will get m by under root of m by 2e by lambda by h cut. Because until unless you don't know what is beta, you cannot use this result. So beta is m by 2e lambda by h cut. That is what your beta is. And very interesting thing that I understand from here is that my beta is inversely proportional to energy. So if my energy increases, my beta will decrease. And if my beta decrease, my transmission will increase. It means if your energy increase, your transmission increase. So more energetic particles will transmit easily. But if your energy is less, you will reflect back. So if you are coming and you are coming with less energy, there is more chances that you will be reflected back. But if you are coming with more energy, there is a more chances that you will transmit. Okay. So what are the things we need to keep in mind? What is the value of B, C, and A? A is A. What is B in terms of A, and what is C in terms of A? What is R and what is T? And all of this is defined in terms of beta. So what is beta? Perfect. So our derivation ends, but we need some extended version of this as well. What I talked about is a potential well, Dirac well. Now I want to compare it with the Dirac barrier. So Dirac well is basically minus delta. So it is basically a well in the ground. But barrier is a positive delta x, lambda into. So it is a wall in front. There is a wall in front. What is, how do we compare them? So there is one bound state exists in this case, as I gave you in the very first page, but there is no bound state which exists in this case. Always remember, if you have this kind of potential, no bound state can ever exist. Perfect. Scattering states are same for both. Scattering states does not change. The reason? Because you see, R and T was depending on lambda square. It was not depending on lambda. So by inserting plus lambda or minus lambda will give you the same result, because the square will absorb the negative sign. So the scattering states are same for both, but the bound states are different. In the well, there is one bound state, but in the barrier, there is no bound state. Perfect. So that was the end of the theory which I want to teach you for this concept. I want to discuss two problems. One June 2024 and one was from the 23. And then you will have much better idea of this concept. Let's understand. So let me zoom and let's read the problem. So the problem is a particle of energy E. So you have a particle of energy E scattered off a one dimension potential. So you see this is a barrier. So when it scatters from the barrier, the transmission amplitude, not transmission coefficient, but the transmission amplitude is T plus. Okay. Now, in a different experiment, the same particle is scattered by one dimensional potential. So now this is well, because you see minus delta x with the transmission amplitude T minus. Okay. In the limit, energy is almost zero, means you are coming with very low energy. What is the phase difference between T plus and T minus? Okay. How do you write T minus? Because we have solved the entire derivation for T minus. You know, first of all, they are talking about the transmission coefficient. So what they are talking about here is, let me show you. Let me show you here. What they are talking about here is this C. This C, right? So yeah, okay. Okay, so they're talking about C. So we should not write iota B here. We should not write iota B here. So that is my mistake. So what we are talking about here is C. So for one experiment, C is 1 minus iota B. So this is for which experiment? Minus lambda delta x. Because we derived this. That C is equals to, so we can even write A here. C is equals to A by 1 minus iota B. What is beta? Beta you can clearly see is this. Now if I reverse it up, if I get lambda into delta x, lambda into delta, then there will be negative sign here. So then my beta will become actually plus. So t plus will actually be a by 1 plus iota beta. So these are my two complex numbers. So this is my first complex number and this is my second complex. What is the phase difference between them? The phase difference between them is 180 degrees. And you need to do this. This is your homework. Okay. This you can try. So the phase difference between two complex number. How to find the phase difference between two complex number is actually class 11th concept. Try it out. What you need to understand is that we did the derivation for minus lambda delta x and we obtained this result. This is my C in terms of A. But when I put it minus lambda into lambda, then here you see there will be a negative sign which will appear up. So beta will become plus beta. So this is my C in case of this potential. Okay. So both of them, in one you see iota, in another you see minus iota. So if you do some mathematics, you will be able to understand that the phase difference between them is actually pi. Scattering states are same, like means their magnitude is same, but their phase are different. Phases in both of them are different. Okay? So that is something you need to understand. That's all. This was your one question. Okay. Another problem. Again, by looking at it, you will see that the question might looks very difficult, but it's not. A quantum particle of mass m is moving in one dimensional potential. This is your one dimensional potential, and this potential is made up of two things. One is a Heave side function, which is theta, and second is a Dirac delta. Well, it's a well because there is a negative sign, so it's a well. Heave side function has a very simple property. Heave side is 1 if x is greater than 0, and if it is 0 if x is less than 0. So basically this is like this. This is like a one stair. So for x less than 0 it is 0, but x greater than 0 it is 1. So if I write my overall potential, so this is my Heave side potential and this is my Dirac potential. Who is dominating? Obviously Dirac. Because this thing, because you can clearly see that now your particle is coming with energy E which is greater than V naught. So you see the height of this well is V naught. Because you see Heave side ke sath who is multiplied? V naught. So the height of the Heave side function is V naught, but your energy is much greater than V naught. So this particle may not even feel this Heave side function that much because energy is much greater than V naught and it is even much greater than lambda. So the dominating factor will be the Dirac potential. You can even ignore Heave side function because that is not going to be your dominating. Because if you carefully see, this is already infinite. If you add V naught in it, it will still remain infinite. So if you add something in infinite, it will still remain infinite. So it is just a simple Dirac potential only. Adding Heave side does not change anything. So it is like you are adding some constant number in infinite. So it will still remain infinite. So it will still remain Dirac potential. Now, what they are asking? They are asking what is a leading contribution to the reflection coefficient. So in reflection coefficient, what is the leading term? So reflection coefficient we have studied is beta square by 1 plus beta square. We know the value of beta. So we put the value of beta as, so what is beta? Let me write here, m by under root of 2e by lambda by h cut. If I put it, I will get m by 2e lambda square by h cut square, and here also you will get the same thing. So it is given that my e is much greater than lambda. So basically this thing is very small than 1 compared to when. This thing is small, but this thing is very small compared to 1. So this I can ignore. So if I ignore this, I am left with this numerator. So what I am left with is m lambda square by 2e h cut. So that is my option number C, m lambda square by 2e h cut square, which was my exact answer. Okay. So that was your question in this case. So these were the two problems of part C, which were very difficult and you might not find the solution anywhere else. It took me some time to conclude this, and you can watch this lecture one more time if you want and try to do this derivation once by yourself. So you can join our courses on Physics by RN for more such knowledgeable material, right? You can visit the website and app. The links are in the YouTube description. Okay. So I will see you all in the next video. That's all for today.